So good morning. Yesterday we have seen the motivation behind learning of discrete time signals and systems. We have also seen the advantages and disadvantages of the use of discrete time or digital systems in processing of analog signals. Just to brief on what we have seen yesterday, I begin the discussion with the repetition of what we covered in the last lecture. The analog system or a continuous time system has an input xt, output represented by yt, and if it is an LTI system, the impulse response of the system represents the system completely. So it is h of t. This is an analog system or continuous time system. Equivalently, this can be equivalently written as a 5-block system. So it is equivalent to this. The first block here is sample oblique hold. Next is analog to digital converter. Third one is a digital signal processor. The fourth one is digital to analog converter. And the last one is a low pass filter, where the input here is x of t, the output here is y of t. These two systems are equivalent. It means I can make use of this digital signal processing systems because of its inherent advantages. It replaces this analog system. Alright? We have also seen the signals at different stages. X of t is the input given to sample and hold. The output of sample hold circuitry is, although I have shown it to be impulses. Alright, so what is it actually? What is the operation of sample and hold? If I do not consider hold, let me only give the output of a sampler. So what is it? It is x of n times t, which is equal to x of t sampled at t is equal to nt. Sampled at means what? I am actually multiplying this by x of t, multiplying it by train of impulses. Which are the impulses? Summation of all those impulses from k equal to minus infinity to plus infinity, delta t minus kt, delta t minus kt, where this t is a sampling time or sampling interval. So it's multiplication of these two signals. When a continuous time signal or analog signal is multiplied by train of impulses, what will happen? This becomes a sampled version, x of nt, which is x of t at t is equal to nt. Are you with me? Now, what is the need of a hold circuitry? A sample needs to be held for a time which is required for conversion from A to D. AD conversion requires some time. Alright, for conversion of that signal, the value must be held for some time, and that is equivalent to conversion time of an ADC. ADC converts an analog signal into digital provided that signal value is constant for a particular duration. That is why I require a sample and hold. Alright. Then ADC converts it into sample values. So here it is, a signal is x of n times t, this signal. The signal here is x of n. What is x of n? Xn is sequence of numbers. In some cases, it may lose the timing information contained in it. Alright, I don't need that information for processing this sequence of numbers. If I have a sequence of numbers, that sequence of number might have been obtained by sampling at x frequency or y frequency or z frequency, but it is actually giving me sequence of numbers. So it loses the time significance in some cases. Then DSP is what? It is a, when we are trying to say digital signal processing, it means it is processing sequence of numbers by using some algorithm. So it's going to be a program running on a general purpose processor, or it's going to be a dedicated hardware in the form of a digital signal processor, which is processing, which is defined, which is designed for a particular task. Say for example, it's a low pass filter, a digital low pass filter, or a moving average filter, or a smoothing filter. Each one of them will have a different algorithm, and this algorithm can be implemented either in the form of a program running on a general purpose processor, or it could be a separately designed processor for the particular purpose. So this DSP could be a general purpose or a special purpose processor. It is processing sequence of numbers. So xn is input to this sequence of number, input to the DSP. What is it going to produce? It produces y of n, which is a processed sequence, processed signal, processed discrete time signal, y of n. Y of n will then be converted into a signal that is similar to a staircase. Alright, that is by using a digital to analog converter, and the staircase signal will have some high frequency signals which are at the edges of the change in the value. That can be removed by using, if it is passed through a low pass filter, you get an analog signal, which is a processed analog signal. This yt and this yt may be the same. If you implement all this equivalent to this h of t, then what you get, this yt and this yt would be the same. So that means this block diagram is used for, is what? Uses concepts of digital signal processing for processing of analog signal. So this is what in general a digital signal processing system would be when you are trying to make use of digital signal processing for processing of analog signal. But in case if the signal is naturally discrete time, in that case you may not require first two blocks and the last two blocks, where the signal is input xn, it is processed by a digital signal processor to produce yn. A naturally discrete time signal, I can get the output also as a discrete time signal. So what you require is only a digital signal processing block. There are some signals which are naturally discrete time. When we count, say, number of passengers on a bus, number of passengers on a train, number of passengers on in a airplane, what are these required for? These are required for forecasting the traffic during a particular time or day, so that the corresponding number of trips of the buses, trains or aeroplanes can be modified, can be increased or decreased based on the requirement. During this slack season, you can decrease the number of trains or flights. If you, during the busy season, you can increase the number of trips from a particular location to the other location, and so on. That decision can be taken on the basis of observation of the traffic for an entire year, and then you take a decision. During this particular season, the traffic is usually going to be there, so you increase the number of trips, and so on. So basically, traffic management, one may make use of discrete time signal processing or digital signal processing. Rain forecasting, if you take a rain forecast, the rain measurement, that can be done, it's actually a continuous time phenomena, but the measurements are done after every hour, after every half an hour, after every minute, after every day, and so on. So some phenomena are naturally discrete time. Alright, in that case, we may not require sample and hold an ADC circuit. Now let us see the classification of discrete time signals. What is a discrete time signal? Once again, they can be classified as deterministic versus random or stochastic. Probabilistic, and so on. These are synonyms. They could be periodic or aperiodic. As I said, deterministic signals are one which can be expressed as a mathematical function, as a mathematical equation, whereas on the other hand, the random signals cannot be represented in the form of a mathematical expression, For example, the speech signal, even if all the speakers are saying the same thing, the speech signal that is recorded in the form of number of samples is going to be different. At different times the values will be different, although the information content in that signal is going to be the same. Periodic, aperiodic, here I may have, so in general discrete time signals are represented by x of n or sometimes as x of nt. You may agree with me that this t is a constant. So a function of n times constant can be written as a function of n itself, right, where n is an integer taking values from minus infinity to plus infinity. So x of n or x of nt, whenever the time significance is wanted, when we want to keep the time significance between xn's, then we make use of the symbol as x of nt. When we don't want that, it doesn't matter. Alright? Now periodic and aperiodic. Here x of n is said to be periodic if x of n is equal to x of n plus minus k times n, where n is the period of this sequence. N is period of the sequence, and this period must be integer. The period has to be integer here because the repetition of sequence cannot occur after 6.3 samples. The number of samples have to be integers. So that must be an integer. K is any other integer. So it means if x of n is equal to x of n plus capital N is also equal to x of n minus capital N is also equal to x of n plus 2n is also equal to x of n plus 3n, and so on. This also equal to x of n minus 2n is equal to x of n minus 3n, and so on. When such is the case, the signal is said to be periodic signal. If such is not the case, then it is said to be an aperiodic signal. Alright, let us take an example now to explain. I have a signal called x of t, which is equal to, say, sine of t. Tell me whether it is periodic or aperiodic in time domain. In the continuous time, sine t is periodic. X of t is equal to sine of n. Check whether it is periodic or not. Is it periodic? Sine of n is constant? No, n is varying. Sine 0, sine 1, sine 2, sine 3, sine 4, sine 5, sine 6, sine 7, sine 8, sine 9, and so on. So sine n is aperiodic. Why it is? Because the argument of sine, if it is multiples of pi, some multiples of pi, then it is going to be periodic. If it is not, then it is not going to be periodic. Although sine t, the sine of n is obtained by sampling sine t, but it is not a periodic signal. After sampling may not remain periodic. Okay, let me explain you. Now to check this, I'm sorry, this must be n. Sine of x of n is equal to sine of n. It's a function of n. Now what is x of n plus k times n? This is equal to sine of n plus k times n. When will this be equal? These two will be equal if k times n is equal to 2p pi, where p is also another integer, integral multiples of 2 pi, then it is periodic. It means what is the value of n? N must be equal to 2 pi multiplied by p by k. Tell me the values of p and k so that I get a value of n This side is integer. P and K are integer. Remember, P and K are integers. 2 pi times P by K. I want it to be integer. Is it possible anyway? For any value of P and K, can the value of n be integer? It's not possible. That is why sin n is aperiodic. Is that clear? Any question? Is that clear? But on the other hand, if I say x1n is equal to sine of 3 pi by 5 times n, 3 pi by 5 times n, is this a periodic signal? Is this a periodic sequence? We can check. Let's find out x of n plus k times n is equal to sine of 3 pi n by 5 plus 3 pi k times n by 5. So x1n will be equal to x1n plus kn if and only if 3 pi k n by 5 will be equal to 2p pi. You understand why I am writing kp? K is integral multiples of n. P is integral multiples of 2 pi. If I take k on both the sides, k gets cancelled. I do not want that to happen. So what is the value of n then? N. So pi now gets cancelled with this pi. And now there is a possibility of 10p upon 3k. For some value of p and k, I am likely to get the value of n to be integer. And that is why this signal is periodic. And what is the period? Tell me. P is equal to 3 and k is equal to 1. Any other? K is equal to 10 and P is equal to 3. Then also you get integer. Okay? All sorts of values. What we need to find out is when you say that a signal is periodic, you are supposed to find out minimum value of n. Minimum value of n for which it is periodic. It can't be 1. So k is equal to 10 and p is equal to 3 are not the correct values, because for n is equal to 1, for capital N is equal to 1, the signal will not be periodic. So the smallest value is when k is equal to 1 and the value of p is something. That is the smallest value of n. So this signal is periodic with period n is equal to 10, not before that. Okay. When n is equal to sine of 3 pi n by 5 x1 of n plus capital N. I take k equal to 1. Simple reason, k equal to 1. So what will happen? Sine of 3 pi n by 5 plus 3 pi n by 5. K is equal to 1. Smallest value of n. Alright? So now 3 pi n by 5 has to be equal to 2p pi, because that is periodic with period 2 pi. If I make only 2 pi, then it becomes 10 by 3. That's not integer. If I make 4 pi, if this is equal to 4 pi, then also it's not periodic. When only this becomes equal to 6 pi. So sine 3 pi by 5 is periodic with period 6 pi. Okay? That is why p must be equal to 3 and k is already taken as 1. So pi gets cancelled and you get n is equal to 2 multiplied by 3 multiplied by 5 divided by 3. So it becomes 10. Let's find out the values. If it is not clear, let's find out the values of sine 3 pi by 5. Sine 3 pi by 5 can be obtained by the angles, various angles, okay. So I'll have to divide this circle into 10 different parts. So pi by 5, 2 pi by 5, 3 pi by 5, 4 pi by 5, 5 pi by 5, no. This is pi by 5, this is 2 pi by 5, 3 pi by 5, 4 pi by 5, 5 pi by 5, 6 pi by 5, 7 pi by 5, 8 pi by 5, 9 pi by 5 and 10 pi by 5. These are angles of pi by 5, 36 degrees. Each of the angle between the lines is 36 degrees. Alright. Now take 3 pi by 5, 1, 2, 3 is here. So this is the value. So what is sine of this angle? You take a sine of 3 pi by 5, you can find out. Then you get 6 pi by 5, this value, 9 pi by 5, 9 pi by 5, then this is 12 pi by 5, then it is this 15 pi by 5 and so on. Like this you get only these angles. Alright. So the sequence value will only repeat after 10 such values. Okay. I hope most of the calculators today have, you can find out the sequence sine of 3 pi by 5 n when n is 0 to 9. Do that. Obtain the value n is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and then sine of 3 pi by 5 n. Find out this angle and then also find out n equal to 10, 11, 12, 13, 14, 15 and so on, and you will see that it repeats after 10. So one example of a periodic signal, x of n is equal to sine of 3 pi by 5 n is an example of a periodic signal. On the other hand, if I write xn is equal to sine of n is an example of a periodic signal. Check whether the following signal is periodic. x2n is equal to sine of root 2n, sine of root 2n. It's also an example of an aperiodic signal. Sine of root 2n. You have to check sine of root 2n plus root 2 into capital N. Root 2 multiplied by capital N, if it is equal to 2p pi, then you get whatever value of n you get as an integer. If you get the value of n to be integer, the signal will be periodic. The sequence will be periodic, but there is no possibility of n. 2 pi p divided by root 2 at any value of p integer, p by root 2 can never be integer. So also n cannot be integer. For any value of p, this right hand side can never fetch you a value of integer. It means the signal is aperiodic. So whatever is applicable to sine is also applicable to cosine. These are real signals. Now I have third signal, that is complex signal, e to the power j pi n. E to the power j pi n. So you check e to the power j pi n plus capital N. This is equal to e to the power j pi n multiplied by e to the power j pi capital N. And we know that complex exponential is periodic with period 2 pi. So when pi n is equal to 2p pi for any value of p integer, if I get n to be integer, I correspondingly get the value of the signal periodic. So for here in this case pi cancels, it is 2. Smallest value of p is 1. So the periodicity here is 2. E to the power j pi n is periodic. Tell me x3n is equal to e to the power j root 2n once again. Obviously it's aperiodic. So you can now check the signals for their periodicity and aperiodicity. Alright? A small exercise. Plot the signal x of t is equal to summation of delta t minus k times t, k going from minus infinity to plus infinity. Small exercise. So it's train of impulses, delta t minus kt, k going from minus infinity to plus infinity. This summation realizes train of impulses. So any signal x of t, a continuous time signal, if it is multiplied by this train of impulses, we get a discrete time signal. Next classification of signals is finite length versus infinite length. If you recollect, length in continuous time is associated with duration. Here, since it is sequence of numbers, the size of the sequence is measured in terms of either a finite length sequence or an infinite length sequence. So xn is said to be of finite length if it contains finite number of samples, x0, x1, x2 and x of 10. This is a finite length sequence with length n is equal to 11 because it contains 11 sample values, 11 non-zero sample values. On the other hand, xn is equal to a to the power n u of n. I will come to u of n little later. U of n is, it is only right sided sequence with reference to n equal to 0. It has the same significance. It is a unit step function that is sampled. Alright, it is called unit sample sequence u of n. This is an infinite duration or infinite length sequence. Alright, let me take this opportunity to define u of n. What is u of n? It is the unit step sequence. U of n is defined as 1 for n greater than equal to 0 and is equal to 0 for n less than 0. This is unit step sequence. Before this I would have written unit sample sequence. It is called as delta n, which is equal to 1 for n equal to 0 and is equal to 0 for n not equal to 0. This is also called, we defined that time as Kronecker delta. The continuous time delta function was known as Dirac delta function. The discrete time delta function is called as Kronecker delta function. Delta n is equal to 1. See here, the value at n equal to 0 is 1. Sample value is 1. That is why it is called as unit sample sequence. Defined as delta n is equal to 1 for n equal to 0 and is equal to 0 for n not equal to 0. So now I can write u of n in terms of delta n and I can write delta n in terms of u of n. Can you write that? Write un in terms of delta n. So u of n is, when you plot u of n, it is 0, 0, 0, 0, 0, 1, 1, 1, 1, 1 and so on, 1. This is a unit step sequence. Unit step sequence. How do you write this as? This can be written as summation of k going from 0 to infinity delta n minus k. That is all. Here there is no concept of t. These are the values of n. This is a sample value delta n. This is delta n minus 1, delta n minus 2, delta n minus 3, delta n minus 4, because these are the sampling instances 1, 2, 3, 4, 5 and infinity. So it is delta n minus k. So u of n is equal to delta n minus k, summation of k going from 0 to infinity. I write this first sample as delta n. What is the second sample value? It is delta n minus 1. What will delta n minus 1? It is equal to 1 for n minus 1 equal to 0. It means it is equal to 1 for n equal to 1. Plus delta n minus 2 plus and so on plus delta n minus infinity. Alright. So I can write it in short form like this. So also I can write what is u of n minus 1. U of n minus 1 will be starting from 1. So unit sample sequence starting from n equal to 1. This is starting from n equal to 0. Prior to this it is 0 here. When I subtract un minus 1 from un, what is left out is only one sample delta n. So delta n can be written as u of n minus u of n minus 1. Alright, with this brief introduction about sequences, let us begin with this is what is time domain representation of sequences. Alright, I can complete it by saying any x of n is sample values for the value of x sequence. X could be a speech sequence, x could be a music sequence, x could be any other sample values taken from the analog signal. This x of n can be written as summation of k going from minus infinity to plus infinity x of k times delta n minus k. Suppose I have some sample values this is some x of n. How do I write this as? What is this value? This is x of k. For this value of k, what is this impulse? Impulse present at this value will be delta n minus k. If it is k is 1, this is delta n minus 1. If k is 2, it is delta n minus 2 and so on. What is the value associated with this? Magnitude of it? It could be called as x of k. So, xk multiplied by delta n minus k, all such summations will represent x of n. So, x of n is x of k, the scalar values, multiplied by the vector, that is location of that x of k. Location is decided by delta n minus k. Where is that x of k present? X of k is always present at delta n minus k. Delta decides the location of the sample value and xk decides the value of the sample. Alright. So, here it is x of 1 delta n minus 1, x of 2 delta n minus 2, x of 3 delta n minus 3, x of 4 delta n minus 4, x of minus 1 delta n plus 1, x of n plus x of 2 minus 2 multiplied by delta n plus 2 and so on. All such summations will give you x of n. Any x of n, any sequence can be represented in this form, a very important relation. There was an equivalent relation in continuous time systems. What was it? It was x of t can be written as integration minus infinity to plus infinity x of tau delta t minus tau d tau. There is always a parallel between continuous time and discrete time systems. Alright. The only difference is this delta t is different than this delta n. Now, we are at the juncture of defining the Fourier transform of discrete time signals. All right. I hope each one of you remember the Fourier transform expression for continuous time signals. So, x of f is equal to integration minus infinity to plus infinity x of t e to the power minus j 2 pi f t dt. We defined x of n to be x of t at t is equal to n t. This t is sampling interval. How is this chosen? This is chosen by using sampling theorem. Which states that a band limited signal with bandwidth twice b can be sampled or can be recovered. A band limited continuous time signal with bandwidth 2b can be recovered from its samples if the sampling frequency used is omega s greater than equal to greater than twice b. This 2b is measured both sides. Actually, it should be b. When I wrote this 2b, it's from minus b to plus b. But positive frequency is only, it's b. Alright. So this says that the Fourier transform of the continuous time signal is minus b to plus b. Some shape I have taken. This Fourier transform, this is the Fourier transform of a continuous time signal. The sampling theorem states that if such signal is sampled at the frequency which is greater than twice b, omega is greater than twice b, then I can recover the original continuous time signal from the sampled values. Alright. So using this, that means what I am doing is, so what is the value of t? T is 2 pi by omega s, sampling frequency. 2 pi by omega s, the sampling frequency. Or omega s is 2 pi by t. Now let us work on the equation, Fourier transform equation. I will not define the left hand side first. Let me only go to right hand side. What is xt becoming? Xt is becoming x of nt e to the power minus j 2 pi f times t. T becomes n times t. And dt is 1. Dt is what? The sample between, the difference between two adjacent samples, which is 1. 2t and 3t, difference is 1. 1t and 2t, difference is 1. 100t, 101t, difference is 1. So dt is not taken. Now this becomes a multiplication. This is a sequence, this is another sequence of numbers. So multiplication of sequence of numbers, I need not integrate. What I need to do? I need to sum it. Sum from what? Sum from n going from minus infinity to plus infinity. And then I play with it. Then I play with the right hand side. How do I, what do I do? I keep this minus j 2 pi as it is, n as it is. Now I have f multiplied by t. What is f? Analog frequency. What is t? T is replaced by, I can also write this as 1 by fs. T is 1 by fs. Fs is sampling frequency. So I can write this t as 1 by fs. Alright. Then I can further define this as e to the power minus j n, and this 2 pi f by fs is defined as small omega. So the right hand side becomes summation of n going from minus infinity to plus infinity, x of n, that t doesn't make sense here. So x of n multiplied by e to the power minus j omega n, and this I define as a new transform called, I define in terms of x e to the power j omega. Compare this with our equation, x of f is equal to integration minus infinity to plus infinity x of t e to the power minus j 2 pi f t dt. This is what is known as CFT, continuous Fourier transform, from, by using sampling theorem, this equation was converted to this equation, which is called as Discrete-Time Fourier transform, also called as Discrete-Time Fourier transform, also known as DTFT. Tell me, after comparison, x has become discrete time. Xn, small xn is discrete time signal. What is this omega? omega is still continuous time because f is continuous time. 2 pi by fs is a constant. F is a continuous variable. Alright, because of f is a continuous variable, omega also is continuous variable. Omega is continuous. So Fourier transform of a discrete time sequence is represented by a continuous function of small omega. Now what is the, we defined small omega as 2 pi f by fs. 2 pi f by fs. Also I can define this as omega by omega s. No change because omega is 2 pi f. When I replace omega as 2 pi f, omega s as 2 pi fs. So omega by omega s is same as f by fs. Alright. Now omega has a unit of radians per second. The unit of omega is radians per second. What is the unit of small omega? Small omega is only radians. This is angular frequency. Omega is an angular frequency. Only measured in terms of radians. See a very important, why it is represented by x of e to the power j omega. I would have well written this as x of omega. Nobody would have stopped me from defining like this. It is in fact a function of omega. Please note that left hand side is capital X, right hand side is small x. So small x is a variable used for time domain representation. Capital X is used for transform domain representation. Why? There is a peculiar reason of why it is written as x of e to the power j omega and not as x of omega. The reason is evident from the fact that this x of e to the power j omega behaves like e to the power j omega. Can you classify e to the power j omega? What is? Can you say something about e to the power j omega? It's a complex exponential. Apart from this, anything else? Any special characteristics of e to the power j omega? E to the power j omega is periodic with period 2 pi. E to the power j omega is periodic with period 2 pi. So also x of e to the power j omega is periodic with period 2 pi. So when I am writing x of e to the power j omega, from x of omega I come to know that x of omega is a function of omega. But when I write it as x of e to the power j omega, I come to know that x of e to the power j omega is periodic with period 2 pi. That is why the notation x e to the power j omega is used. Now let us prove that x of e to the power j omega is indeed periodic. So x of e to the power j omega, when I say it is periodic, so I would write it as x of e to the power j omega plus 2 pi, 2 pi k. This will be equal to, now I write only right hand side. So everywhere omega is replaced by omega plus 2 pi k. So summation of x of n e to the power j minus j, omega is replaced by omega plus 2 pi k times n. N going from minus infinity to plus infinity, which is equal to summation n going from minus infinity to plus infinity, x of n e to the power minus j omega n multiplied by e to the power minus j 2 pi k n, and this function is always equal to 1. This means this is same as x of e to the power j omega. So x of e to the power j omega, very important characteristics of DTFT, that it is periodic with period 2 pi. It It is periodic with period 2 pi. Any questions so far? Yeah. Discrete time Fourier transform of any sequence is going to be periodic. There was nothing new in this. You already have studied sampling theorem, and this is the outcome of a sampling theorem only. Let's see what I am trying to compare, how I am trying to compare this with the Fourier transform of a continuous time signal. The sampled version x of, when you sample a signal x of t, you get x of nt, and Fourier transform of x of nt is periodic, right? Let's see. I know some x of t, say it is having a Fourier transform noted by this, which is minus b to plus b. This is a band limited signal. Assuming that this is a band limited signal, take its Fourier transform, it will be minus b to plus b. Now I sample this, that means I take x of nt. What will happen to its Fourier transform is the question. Alright. Now what is this? This is capital T. The distance between two is capital T. So how is x of nt formed? X of nt is formed as multiplication of x of t with train of impulses. This is multiplication. Train of impulses is what? K going from minus infinity to plus infinity, delta t minus k times t. Here it is multiplication. Now what is the Fourier transform of a train of impulses? So Fourier transform of train of impulses, summation of delta t minus kt, k going from minus infinity to plus infinity, is 2 pi times Fourier transform of a train of impulses is another train of impulses. So it is 2 pi times k going from minus infinity to plus infinity, delta, on this axis it is omega minus omega k times omega s. K times omega s means 2 pi k divided by t. 2 pi by t is omega s. So this is same as 2 pi times summation of k going from minus infinity to plus infinity, delta omega minus 2 pi by t times k. The train of impulses, that is, each sample is with a distance of capital T here, then its Fourier transform is train of impulses. But what is the distance between the two impulses? It's 2 pi by t. Smaller is the distance here, larger is the distance in the frequency domain. Duality property. Larger is the distance here, smaller is the distance in the frequency domain. Very important result. Fourier transform of train of impulses is train of impulses. Alright? I will explain this once again with proper examples. At this point of time, using this relation, I want to prove something else. So let us use this relation first. So we have seen this xt has this Fourier transform. This is important to us. So this is what is our x of j omega. Since I am using j omega here as well, I must use j omega here. This is right hand side is a Fourier transform of train of impulses. Now what happens? In the time domain, they are getting multiplied. So what happens in the frequency domain? They get convolved. So do convolution of this with train of impulses. So this train of impulses can be plotted. This train of impulses can be plotted as magnitude is 2 pi. And what is the separation here? This separation is 0. The next separation is 2 pi by t. So this is omega s. This is twice omega s. This is thrice omega s, and so on. This is minus omega s. This is minus 2 omega s, and so on. Magnitude is 2 pi. What is this? 2 pi delta omega. 2 pi delta omega minus omega s. 2 pi delta omega minus 2 omega s. 2 pi delta omega minus 3 omega s. All such impulses are added to form this signal. Now what we want to do is, we want to take convolution of these two. Don't bother about the magnitude much. Alright? Now what is the convolution of these two? The convolution will be dependent on what? On the separation. On this separation. So this convolve with this impulse will give me one image of the Fourier transform like this, which is from minus b to plus b. This convolve with the second impulse will give me another image around omega s. This is omega s, this value is omega s minus b, this value is omega s plus b. The convolution of this with an impulse is that function present as surrounding 0, surrounding omega s, surrounding 2 omega s, and so on. Alright? Similarly, on the left hand side, it will be like this. What is this value? Minus omega s. What is this value? Minus omega s plus b. What is this value? Minus omega s minus b. So the Fourier transform of a sampled version is periodic with period omega s. With period omega s. What is this scale? This scale is still omega. This scale is omega. If I want this scale to be small omega, what will it become? This small omega is 2 pi times omega divided by omega s. So when this omega s, when this small omega, this omega is equal to omega s, what happens? This becomes 2 pi. So this becomes 2 pi. This remains 0. This becomes minus 2 pi. Next instance of the Fourier transform will exist at 2 omega s. 2 omega s is equivalent to 4 pi. So these red colored things are small omega axis. This is small omega. These are the values of small omega. So small omega always will remain in radians. Capital omega values are omega s, 2 omega s, and so on. So friends, we are trying to prove logically the sampling theorem. Now if suppose I pass this signal with this Fourier transform, I pass it through a low pass filter. When I pass these sampled values through a low pass filter with this frequency response, what do I get? I get the original, only this one copy. Multiple copies of the Fourier transform here can be converted to a single copy if this signal is passed through a low pass filter. Alright? That means these samples, if they are passed through a low pass filter, I can get the original signal back. This is the sampling theorem. Now what we are trying to prove is, this is possible to recover the original single copy, can be recovered only if this separation, what is the separation? Omega s minus b this value must be greater than this value. Omega s minus b must be greater than b. Means what? Means omega s must be greater than twice b. This is the sampling theorem. In the separation here, if this is not separate, that means if omega s is less than twice b, then what? How will this look like? This looks like one copy here, another copy here, third copy here, and so on. This is 0. This value is omega s. This value is omega s minus b. This value is capital B. So what I am saying here, this is the instance when omega s minus b is less than b. Then the actual Fourier transform look like this. Up to this it is same, then it is constant, then it is same, constant, same, and so on. Now when this signal is passed through a low pass filter, I will not be able to recover the original signal back. So it means this is not true. When such is the case, the signal cannot be recovered. Signal can only be recovered, the original signal can be recovered if omega s minus b, this value, if it is greater than b, then only it is possible to recover the original signal. Then only I can get back the triangle, which is the Fourier transform of the continuous signal. This can be recovered only if this omega s minus b is greater than b, otherwise not. You understand? I repeat this once again with reference to omega axis and capital omega axis. When I write this as capital omega, this is what is on the x axis here, what is on the y axis here? It is x of e to the power j omega. But the relationship is, what is omega? Omega is 2 pi times omega by omega s. So it means I can draw the plots with reference to small omega or capital omega. If I write with reference to capital omega, this is the axis, this is how axis looks like. The axis becomes, this axis is omega, plot remains the same, but what will change? This omega has becomes 2 pi, twice omega has becomes 4 pi, 0 remains 0, minus omega has becomes minus 2 pi, and so on. Now what will this central value become? If this central value here is omega s by 2, central value here is minus omega s by 2. With reference to omega s, the values are minus omega s by 2 to plus omega s by 2. 1 omega s. Bandwidth is 1 omega s. This omega s by 2 becomes, with reference to small omega, it becomes minus pi. Plus omega s by 2 becomes plus pi. So friends, like when we draw Fourier transform in the continuous domain, the bandwidth is measured from minus b to plus b. So what is the bandwidth? Bandwidth is actually b. Only positive frequencies are considered for measurement of bandwidth. Here the bandwidth is minus pi to plus pi or 0 to 2 pi. Alright. So make an important outcome of our discussion that x of e to the power j omega is periodic with period 2 pi. Also bandwidth of discrete time signals is 2 pi. It is enough. Bandwidth of discrete time signals is 2 pi. A very important conclusion. What is the bandwidth of speech signal? We say 5 kilohertz, 4 kilohertz. What is bandwidth of audio signal? 20 kilohertz. What is the bandwidth of video signal? 5 megahertz, and so on. What is the bandwidth of a biomedical signal? About 100 hertz. 100 hertz. All right. Now all these signals can be sampled by different sampling frequencies omega s. Different sampling frequencies omega s. All are going to produce sequence of numbers, but the bandwidth of this sequence of numbers is always going to be 2 pi. So with reference to bandwidth of digital signals or discrete time signal, the bandwidth is said to be equal to 2 pi. That is the outcome of discussion of DTFT. All right, we will talk about this in more details in future. All right, thank you.